Hundreds of hydrogen projects have been announced around the world. Many have impressive capacities, major corporate partners, and ambitious timelines. But announcement is easy. Reaching a final investment decision is much harder. That makes this project particularly interesting. Barrow Green Hydrogen in the United Kingdom is a 30-megawatt project that reached final investment decision in 2026. So in this investigation, we're not going to focus mainly on the electrolyzer. We're going to ask a much more important question. What was different about the way this project was built that allowed it to reach FID while so many other hydrogen projects remain stuck on paper? And more importantly, are there lessons here that other hydrogen developers can actually use? This is the first thing we need to understand. A hydrogen project announcement is not evidence that the project will actually be constructed. Think about the development pathway. A project moves from announcement to concept to feasibility to development, then perhaps to final investment decision, construction, and eventually operation. At every stage, projects disappear. The IEA's Global Hydrogen Review 2026 illustrates just how dramatic the filtering process has become. Around 27 million tons per year of hydrogen production had been announced for 2030, but only around 6 million tons per year was considered likely, and the outlook itself was cut significantly in just 1 year. So when a company announces a 500 megawatt or 1 gigawatt hydrogen plant, that isn't the end of the story. It's the beginning of the test. So what actually eliminates these projects? Usually, it isn't because electrolysis suddenly stopped working. The problems are much more ordinary. There may be no credible customer willing to buy the hydrogen. Electricity may be too expensive. The site may look attractive on a renewable energy map, but lack water, land, grid capacity, or infrastructure. Transportation costs may destroy the economics, or the project may simply fail to attract financing. This leads to one of the most important ideas in this investigation. Hydrogen projects usually fail as systems, not as electrolyzers. The electrolyzer can work perfectly while the overall project still makes no economic sense. Now let's look at the project that survived. Barrow Green Hydrogen is a 30-megawatt PEM electrolysis project in the United Kingdom. The project is expected to produce roughly 100 gigawatt-hours of hydrogen per year. The customer is Kimberly-Clark, which operates a tissue manufacturing facility in Barrow-in-Furness. And in May 2026, the project reached final investment decision. Those are the published project facts. But those facts alone don't explain why the project survived. So the question becomes, what did Barrow get right that allowed it to move through the development funnel? Instead of starting with the electrolyzer, we're going to reverse engineer the entire project. We'll examine it through 7 development questions. First, define. What problem are we actually trying to solve? Second, screen. Does the location work? Third, design. What system actually serves the customer's need? Fourth, model. Does the economics make sense? Fifth, stress test. What happens when the assumptions get worse? Sixth, validate. Are the customer, contracts, and project assumptions real? And finally, prepare. What evidence is still required before the project can move forward? These 7 stages will form the backbone of this investigation. The first stage is defining, and this may be one of the most important lessons from Barrow. The project did not begin with someone saying, "We want to build a hydrogen plant." It began with an industrial problem. Kimberly-Clark operates a tissue mill. That mill requires heat and steam. Today, much of that heat comes from natural gas. The company also has a decarbonization objective. So the real problem is not hydrogen production. The real problem is, how do we reduce fossil gas consumption while continuing to supply reliable industrial heat? Hydrogen became one possible solution to that problem. And that's an important distinction. Good projects begin with a problem. They do not begin with a technology looking for somewhere to be used. Now compare two completely different project development approaches. In the speculative approach, developers begin with hydrogen production. They secure land. They choose an electrolyzer capacity. They announce a large project. And then they start searching for someone willing to buy the hydrogen. That creates enormous commercial risk. Barrow worked in the opposite direction. The industrial customer already existed. The energy demand already existed. The steam demand already existed. The hydrogen project was designed around that customer, so the market did not have to be invented after the project was announced. The demand came first. Hydrogen came second. That greatly changes the risk profile. So let's test the first case. Was the problem defined? Yes. Was the customer identified? Yes. Was the hydrogen use case defined? Yes. And did real industrial demand already exist? Yes. That does not guarantee that the project works, but it does eliminate one of the biggest uncertainties affecting speculative hydrogen developments. So, on our ReneEnergy development framework, Barrow passes the defying gate. Now we move to screen. A screen asks whether the location actually supports the project. This is where hydrogen siting becomes much more complicated than simply finding strong wind or solar resources. At Barrow, several things needed to coexist. There was industrial demand. There was a renewable electricity pathway through a long-term agreement with SEFE. The project needed land. It needed water. It needed a grid connection. And perhaps most importantly, the customer was effectively next door. This matters because a location with excellent renewable resources can still be a terrible hydrogen site. A strong wind resource cannot compensate for a non-existent customer. Cheap solar cannot compensate for impossible infrastructure. Hydrogen siting is a systems problem. And proximity matters far more than people sometimes realize. Hydrogen has to move from where it is produced to where it is consumed. Every kilometer can introduce additional cost. You may need pipeline infrastructure, compression, storage, transportation equipment, safety systems, and additional operating costs. All of those eventually appear in the delivered cost of hydrogen. So a project might produce very cheap hydrogen at the electrolyzer outlet and still deliver expensive hydrogen to the customer. Barrow avoids much of that problem by pairing production with a nearby industrial user. The important lesson is simple. Cheap hydrogen production does not automatically mean cheap delivered hydrogen. Now let's test the screening gate. Demand? Clear. Location? Clear. Power pathway? Also reasonably clear. But at this stage, two major questions are still unresolved. The first is economics. Can hydrogen actually compete with the incumbent fuel? The second is commercial structure. Who carries the different risks, and how are the contracts structured? Those questions still need to be answered, but there is enough alignment to move the project into design. Now we get to the electrolyzer. Notice how late in the development process the technology appears. Barrow uses 30 megawatts of PEM electrolysis, configured as 6 5-megawatt plug power Geneco units. But the important point isn't simply the technology brand. The system configuration follows the project requirements. The expected power profile matters. Hydrogen output matters. Operational flexibility matters. And most importantly, the customer's demand profile matters. The project requirements determine the technology configuration, not the other way around. That is very different from selecting an electrolyzer first and then trying to build an entire project around it. This leads directly to the next development lesson. Size the project backward from the customer. Start with the heat demand. Then calculate how much hydrogen would be required to replace the targeted amount of natural gas. From that, estimate hydrogen production requirements. Then determine electrolyzer capacity. Then storage requirements. then delivery, then boiler integration. This sounds obvious, but many projects start with a headline number instead: 100 megawatts, 500 megawatts, 1 gigawatt. Why? Because those numbers sound impressive, but impressive capacity does not automatically create a viable project. The system should be sized around the actual demand. That's exactly the logic shown on slide 13 of the deck. Now the system architecture becomes clear. Renewable electricity feeds the electrolyzer. The electrolyzer produces hydrogen. Hydrogen is delivered locally. The hydrogen is integrated into the industrial boiler system, and the boiler produces the steam required by the tissue mill. Technically, this chain is possible, but this is where many energy projects make a critical mistake. They assume that because something is technically possible, it must also be economically viable. Those are two completely different questions. So we pass design and move to model. This is where the economics become interesting. Barrow is not really competing against another green hydrogen project. Its primary competitor is natural gas. The tissue mill already uses gas, so hydrogen has to create enough value to justify replacing part of that existing fuel. Published project announcements indicate that the project could displace up to 50% of the site's natural gas consumption and avoid approximately 18,300 tons of carbon dioxide emissions annually. But economically, the real question becomes, what must hydrogen cost for this replacement to make sense? That is the benchmark, not another hydrogen plant, the incumbent fuel. When we model hydrogen production economics, many variables matter. Electrolyzer CapEx matters. Efficiency matters. Financing costs matter. Maintenance matters. But two variables often dominate: electricity price and utilization. Electricity is the main operating input for electrolysis. So if electricity becomes expensive, hydrogen becomes expensive. At the same time, an electrolyzer that operates only occasionally has to recover its capital cost over fewer kilograms of hydrogen. That pushes cost higher again. This cost driver ranking is ReneEnergy analysis rather than published Barrow financial data. But the broader lesson is important. A cheap electrolyzer cannot rescue expensive electricity. Now we reach one of the most important pieces of the story. Barrow holds a UK hydrogen production business model contract awarded under HAR1. That support matters, because we need to distinguish three very different statements. Statement 1. The technology works. Statement 2. The project economics work with policy support. Statement 3. The project economics work without policy support. Those statements are not interchangeable. A project reaching FID does not automatically prove that green hydrogen has become cheaper than natural gas on an unsubsidized basis. Policy can close part of the gap, and in emerging industries, that can be exactly what allows projects to move from concept to construction. So FID should never be confused with subsidy-free competitiveness. Now we reach stress test. A base case financial model can make almost any project look attractive if every assumption behaves perfectly. Real projects don't work that way. So instead of asking whether the base case works, we ask, which assumption breaks the project first? What happens if electricity prices increase by 30%? What happens if electrolyzer utilization falls 20%? What if natural gas becomes 30% cheaper? What happens if project CapEx rises 20%? And what happens if government support is reduced? These are illustrative ReneEnergy development tests. They are not published Barrow financial results. But this is exactly the type of questioning a serious project needs before capital is committed. This is why one attractive LCOA number tells you surprisingly little. A base case assumes electricity prices behave, utilization behaves, CapEx behaves, financing behaves, construction behaves, and the customer behaves. But projects rarely experience perfect conditions simultaneously. The real test is what happens when several assumptions move against the project at the same time. That's survivability. A project that only works under one perfect scenario is fragile. A project that continues to function across several plausible scenarios is much more robust. So project lesson number 5 is: survivability matters more than one attractive LCOE number. Now we reach FID, and this may be the single biggest dividing line between hydrogen projects that advance and hydrogen projects that stall. Offtake. Someone has to buy the hydrogen, not merely express interest, not sign a press release, not participate in a memorandum of understanding. A financeable project needs credible revenue visibility. A supply agreement gives lenders evidence that future hydrogen production actually has a market. Without that, financing becomes extremely difficult. So project lesson number 6 is: someone has to buy the hydrogen on terms that a lender can accept. And now we arrive at final investment decision. FID is not one thing. It is the moment when multiple pieces align at the same time: technology, site, power, customer, offtake, policy, economics, and financing. That alignment allowed Barrow to reach FID in May 2026, with operation targeted for 2028. But there is another distinction we need to make. FID does not guarantee that the project will be completed on time. It does not guarantee the final construction cost, and it does not guarantee operational success. FID is a major development threshold. It means enough uncertainty has been resolved for investors to commit capital. That is very important, but it isn't the end of project risk. So what did Barrow appear to get right? Not one magical technology, not one exceptional electrolyzer, not one spectacular renewable resource. It was the combination: real industrial demand, a suitable site, a system designed around that demand, economics that could work within the policy environment, a credible offtake structure, and government support that helped close the remaining economic gap. The important phrase here is all at once. Remove one critical piece, and the development path can stop. That is why hydrogen projects should be treated as interconnected systems rather than collections of equipment. Now apply the same framework to your own project. Define: who actually needs the hydrogen? Ask green. Does the location work when you consider power, water, infrastructure, customer proximity, and logistics together? Design: what system configuration best serves that demand? Model: what does the hydrogen actually cost? Stress test: which assumptions break the economics? FID: is the demand real and commercially credible? And prepare: what evidence is still missing before the project should move to the next stage? These are 7 simple questions, but they expose a surprising number of weak projects very quickly. And this is the reason we built H2 Hub. H2 Hub takes this same project development logic and makes it usable as a guided process. Define the project. Screen potential locations. Develop the system concept. Model project economics. Stress test the assumptions. Validate the critical evidence. And prepare the project for the next development stage. The objective isn't simply to generate another hydrogen calculation. It is to help developers understand why a project works, where it is vulnerable, and what evidence is still missing. But there's an important boundary. H2 Hub is decision support before detailed professional engineering. It does not replace feasibility studies, FEED, permitting analysis, engineering design, or lender due diligence. So let's return to the question we started with. Why did Barrow Green Hydrogen reach final investment decision while so many hydrogen projects have not? The answer isn't that Barrow discovered a revolutionary electrolyzer. And it isn't that hydrogen suddenly became universally cheaper than natural gas. The answer is more practical. Enough pieces of the project worked at the same time. The problem was defined. The location worked. The system was designed around a real customer. The economics had a credible pathway. The assumptions could be evaluated. The demand was validated. And enough evidence existed for the project to reach investment decision. That is the bigger lesson. Successful hydrogen development isn't about finding the biggest project. It's about systematically eliminating the reasons the project could fail. And that leaves one question for every developer watching. Would your hydrogen project survive the same test? H2 Hub by ReneEnergy is designed to help you start answering that question, step by step.